So in this video I'm just going to talk a little bit about the background to creating both an OpenGL context and how we can approach this using WebGPU. So this first example, as you can see, is inheriting from QOpenGLWindow, which is part of the PySide Q OpenGL module. And basically what this does is it gives us a full screen main window application with a QOpenGLWidget basically as the central widget in there. So there's nothing else in there at all. It provides a number of methods, in particular initializeGL, then we have paintGL, and then we have resizeGL. There are a few others as well, but these are the core ones I'm going to concentrate on. So the idea is that initializeGL is called once, and it's called after the window has been created, so that OpenGL can then create a context and associate the widget with that window. Under the hood, as we'll see with the WebGPU widget, which I'm going to show you later, effectively what it's doing is it's creating a frame buffer for OpenGL to render into, and then those pixels are what eventually ends up on the screen for us. Typically what we'll do in this one is we'll do any once-off initialization, so setting modes, loading shaders and things like that. Typically we'll start all our timers in here. It's not so much an issue in the C++ version, but in the Python version, in the C++, if you start a timer and try and call a draw before we've initialized OpenGL, it does actually cause call dumps of programs. So this is a good habit to get into. Now, resizeGL is called once every time the window is resized and the new window width and height's passed in. Again, typically all we do here is set the new window width and height in there, which we'll use later when we resize our viewport for drawing. And in this case, I'm updating the projection matrix as well, just so that that's ready to be used when we render. And then finally, paintGL is called every time a repaint is required. In this case, that repaint happens when update is called, and OpenGL has that on a timer. It is locked by default, I think, to VSync, so it should be about 60 FPS. And this is where we do our core drawing. In this case, we're just going to draw some lines and so on. We typically make this the current context active. We also have to take into account a number of other things. If we are using things, more advanced features like frame buffer objects, then we have to enable to make sure that we've got the correct frame buffer object bound, because under the hood, OpenGL is used in rendering in a lot of the Qt widgets and things like that as well. So you have to make sure that you're in the correct version for it to use. So in this example, it's very simple. It just runs the lines there. You'll notice that it's not fully resized there. That's just a bug in my dual monitor display that I'm rendering this on the big monitor, and the small monitor has got a different aspect ratio because of the MacBook pixel aspect ratio. That also causes issues with aliasing and things like that because it's set up for a different screen size. It's much more noticeable, as we'll see later when we do the WebGPU version. So in WebGPU, what I've done is I've basically created a widget to do something similar to the OpenGL widget. In fact, I'm using similar naming conventions. Now, under the hood here, what's happening is I'm creating a buffer that is designed for rendering to the screen. Now, there's a few issues with how WebGPU works under the hood, that it requires buffers to be of a particular size and a particular number of pixels to copy the data to and from, which we'll see in a little while. But under the hood, when we initialize here, what we do is we have this frame buffer here, which is what we're going to render to in the end. We have a timer. Basically this timer is just connected and started off to try and get us our 60 frames per second. We store the device pixel ratio. Again, this is in particular for Macs when we've got Retina displays which have different ratios to normal displays. And you can see here I'm calling this initialize buffer method here. An initialize buffer is basically going through here. It gets the width and the height based on the ratio and the current window width and height when we've created it. We then generate an empty buffer of RGBA pixels, so basically height by width by 4 of unsigned integer 8 bytes. That can be easily then converted into a Q image and blitted to the screen, which is what we're doing later. I'm also storing this as a class attribute which is used in the WebGPU side later on. And then we've got a series of other methods. So the core methods that are built in here is resize WebGPU. This is analogous to the resize GL, and basically we must implement that in any class that's inheriting to use it. We have a resize event. This resize event gets called by Qt within the widget. So what happens here is I will automatically capture this event that Qt issues, and then I update the widths and the size. Then we call resize WebGPU here, which is our local update, the changing projection and things like that typically. And you'll also notice that I call this create render buffer here. And what create render buffer is going to do is it's going to update our new render buffer. So this is our buffer that we're going to use to render into. By default, we are going to create a multi-sample texture. So we're going to enable multi-sampling. There's some details of this in a later lecture. But basically, we have a large texture buffer that is used here. So we have the sample count, and then that gets resolved down to this color buffer texture, which is the one that we finally display in the end. And we also add here a depth texture. So we've got depth texturing, and we have a final aligned buffer here that we're using for copying to our Q image. And this is the important thing. So this aligned buffer, there is a couple of functions in here. What we do is we calculate the aligned row size for our texture copy operations. So the data needs to be aligned on a boundary of either 256 bytes or 512 bytes, depending on what we're doing. In WebGPU case, it's 256. So we determine a row size here, and then we go through and we basically repad our buffer here so that we've got the correct size of data when we're reading it from WebGPU. Effectively, we'll always have an oversized buffer to render to, but we can copy it efficiently in these chunks of 256. And then what we have to do when we copy the data back to render it is, as you can see here, we have to grab the strided data to ignore the padding. So the copy back is done, aligned to a boundary, and then what we do is we convert that now into our strided data array here using some NumPy tricks, which is great. It's all nicely built into NumPy. And then that is what gets copied into our frame buffer, which then gets presented to the screen in this bit here. So what you can see here is we create a Q image, and then we blit that Q image to the screen, and then we render the text. You'll also notice the text rendering is built into this. It has the ability to resize the text and everything else based on the screen size. So WebGPU is a little more complex than the OpenGL version, but it does now allow us to resize our widgets nicely and do various different bits. You can notice I've got some aliasing there, which is pretty bad. Once we get to the full screen size there is an unaliased version. Again, it looks far better on other displays than this display, unfortunately, but that should be slightly more unaliased, but we're still getting aliasing in there. So have a look through that code and try and get a feel for how it all works, how the text rendering's working, and how this bit is working as well.